when I mention plane here, we're typically going to be working in the XY plane. So problems that can benefit from plane stress will be typically thin, members with loads applied in the plane only. And I want to mention here, when I say thin, I mean that the Z dimension is small compared to X and Y. For a case of plane stress, as the name implies, we're going to have stresses that are acting in the XY, and we're going to assume all the stresses that are related to Z are equal to 0, right? So I will have a sigma X, will have a value. I will have a sigma Y. I can have a tau XY, but sigma Z is going to be equal to tau Zx or Xz equal to tau Yz or Zy equal to 0. On the other hand, for plane strain, still working in the XY plane, this type of analysis is for long bodies in the Z direction. With the same cross-section cross-sectional area, with loads acting only in the X and or Y directions. So in the plane of that cross-section, and do not vary in the Z direction.
Would plane stress, would that apply to like pressurized tanks? Like hoop stress, hoop strain, is that kind of the same idea or no?
Yeah, tanks could have, if they have like end caps, then they would also have stresses in the longitudinal direction. So that do not directly apply. Now, when we are looking at a case of a plane strain, we can only, or we can use only one unit thickness or length need to be considered. And as the name implies here, plane strain, meaning that the strains are only going to be acting in the XY direction and we're going to assume the strains outside of the plane are all going to be equal to 0. So I'm going to have an epsilon x that's going to have a value, can have an epsilon y, I can have a gamma xy, but my epsilon z is going to be equal to gamma xz equal to gamma yz equal to 0. To the state of stress, and you've seen that before in solid mechanics. I can use an infinitesimal element to represent a 2D state of stress. So if I'm working in the XY plane, this is my X face, and on my X face, I'm going to have a normal stress, sigma X. This represents my positive Y face, and I can have a sigma Y. And of course, this is the negative X face is also going to get a sigma X. Negative Y face is also going to get a sigma Y. And I'm also going to see a positive tau XY on the positive X face, and a positive tau YX on the Y face, and the same on the negative faces. Equilibrium of this infinitesimal stress element, we can show that tau YX is the same as tau XY. Therefore, we have only 3 independent stresses, namely sigma X, sigma Y, and tau XY. These independent stresses may be represented by a stress vector. Sigma, where sigma is equal to sigma X, sigma Y, and tau XY. For that state of stress, from strength of material or solid mechanics, we were able to find the maximum normal stress and the minimum normal stress. We call that sigma max the major principal stress, and we call that minimum the minor principal stress, where sigma 1 was equal to sigma X plus sigma Y over 2 plus the square root of sigma X minus sigma Y over 2 squared plus tau XY squared. And sigma 2 was sigma X plus sigma Y over 2 minus the square root of sigma X minus sigma Y over 2 squared plus tau XY squared. Sigma max and sigma min, or sigma 1 and sigma 2, are principal stresses. These principal stresses are going to occur at a principal angle theta p, where tan 2 theta p is equal to 2 tau xy divided by sigma x minus sigma y. Meaning if I'm starting with the horizontal vertical as my x, y direction, in order for me to get these major minor principal stresses, I will have to rotate my element along the, if this is my x direction, I'm gonna have to go like an angle theta p to get my sigma 1 and my sigma 2, sigma 1 and sigma 2. And it is important to note that corresponding to principal stresses, we have 0 shear stresses, right? So when I get to the state of principal stress, I do not get any shear stress components. And you may recall Mohr circle, the graphical method to find the stress at any given angle or to find the principal stresses. So this is a quick review of the 2D state of stress. I'm going to do the same for a 2D state of strain. So if I'm starting with an element in plane, so we are still working in the x, y plane. If I have plane strain only, this element will displace in plane and will also get distorted. So it's going to look something like this upon distortion. And we are going to get normal strains, epsilon x and epsilon y. The displacement along the x-axis is measured by u, and the displacement along the y-axis is measured by v. So we'll see here that if I call this corner point A, this displaced distance u if I measure the distance here to B, I see here a displacement that will be equal to u plus du by dx times dx along the x-axis. If I call this point C and measure the distance that it moved from its original position, I will have here, of course, A displaced distance V, and this has displaced distance V plus dV by dy times dy, where of course the infinitesimal block has dimensions dx by dy, right? So I can come here and say epsilon x is equal to du by dx, and epsilon y is measured by dv by dx. And I also have a shear strain gamma xy that is equal to du, the partial derivative of u with respect to y, plus dv with respect to x. This gamma xy may be also described as the change in the right angle between x and y. And of course, like we described a stress vector using a column matrix, I can also write a strain vector using a column matrix where this epsilon will be equal to epsilon x, epsilon y, and gamma xy. In order to drive stress-strain relationships, I'm going to draw upon the 3D stress-strain relationship that you can find in Appendix C in the textbook, where sigma x in 3D, if I write the stress vector, I will have sigma x, sigma y, sigma z, tau xy, tau yz, and tau zx. These are related to the strains epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, and gamma zx. By the matrix D, which is equal to E divided by 1 plus nu multiplied by 1 minus 2 nu. And here I have a 6 by 6 matrix.
1 minus 2 nu.
Correct. 1 minus nu. I have here in u, and there are going to be many zeros. I have here 3 zeros. And then it's a symmetric matrix. I have here 1 minus nu, 0, 0, 0. Well, of course, nu is Poisson's ratio, right? 1 minus nu, 0, 0, 0. I have here 1 minus 2 nu over 2, 0, 0. And 1 minus 2 nu over 2 and 0. And finally, 1 minus 2 nu over 2. And this is a symmetric matrix. This here may be written as sigma equal to D times gamma. I'm sorry, epsilon. Where D is known as the stress strain matrix, or the constitutive matrix. E is the modulus of elasticity. And nu is Poisson's ratio. By the way, this is equation C310 in your textbook. So it's in appendix C. We are going to apply this equation to plane stress and plane strain. So for plane stress, we have sigma z equal to tau xy equal to tau yz equal to 0. When I apply C310, we will find that gamma xz is equal to gamma yz equal to 0, but epsilon z, for a case of a plane strain, is not a plane stress, I'm sorry, is not equal to 0. But if we're interested only, or if we only have the plane stress, sigma x, sigma y, and tau xy, we can relate these to epsilon x, epsilon y, and gamma xy using E over 1 minus nu multiplied by 1 nu 0, nu 1 0, 0 0, and 1 minus nu over 2. I can spell out the constitutive matrix for a case of plane stress. D is equal to E divided by 1 minus nu multiplied by 1 nu 0, nu 1 0, 0 0, and 1 minus nu over 2. for plane strain, we have epsilon z equal to gamma xz equal to gamma yz equal to 0. Again, if we apply C310, we'll find that tau xy equal to, tau xz is equal to tau yz is equal to 0. But sigma z is not equal to 0, even though I'm not including it in equations. Question.
First line for the plane stress, was that supposed to be tau xy is equal to 0?
Yeah, for plane stress, no, you are correct. This is tau xz. Thank you. Yeah, of course, tau xy is not equal to 0. And again, it's important to note here that even though epsilon z is not equal to 0, but I'm not including it in the relationship. Focus on the plane stress, plane strain relations. Likewise, we're going to do here the same for plane strain. So I'm going to get the relationship sigma x, sigma y, tau xy is equal to E divided by 1 minus nu multiplied by 1 minus 2 nu multiplied by 1 minus nu 0, nu 1 minus nu 0, 0, 0, 1 minus 2 nu over 2 multiplied by epsilon x, epsilon y, and gamma xy. And this portion here makes my constitutive matrix D. So we have used the 3D stress-strain relationship to derive the plane stress-strain relationship, as well as the plane strain stress-strain relationships. We have used the governing differential equations for bar elements, for beam elements. And I want to give you here the basic partial differential equations. For plane stress. And these are from Timoshenko's book that was published in 1970. d2u partial derivative with respect to x squared plus d2u dy squared is equal to 1 plus nu divided by 2 multiplied by d2u by dy squared minus d2v by dx dy and d2v dx squared plus d2v dy squared is equal to 1 plus nu over 2 multiplied by d2v by dx squared minus d2u dx dy. So this covers the needed background from theory of elasticity for plane stress, plane strain, and the stress-strain relationships that we are going to need as we derive the plane stress element equations. So we're gonna get started. I think we're probably going to take more than one session to derive these equations, but let's get started, and we are going to follow the same